Hello guys, you're welcome back to our class once again today. In this particular class, we're going to be bringing you an experiment to deduce the mass of a substance, in this case the meter rule. And to do that, we'll be needing two retort stands, as you can see here. We'll also need two threads that we're going to be using to mount on the retort stands to be able to balance the meter rule horizontally. Before we commence, we also have a stopwatch, a knife edge, and some sets of masses here, and another meter rule we use in measuring the length of the thread. Now, before we commence, we would have to find the center of gravity of the meter rule. Okay, so here we are asked to find the center of gravity of this meter rule, and we have here that as you can see here, my meter rule is balanced at approximately 50 cm, as you can see here. So here is my center of gravity for this particular meter rule. So here is it horizontal. We find the center of gravity to be at exactly 50 cm. And at that point, which is the center of gravity, we are going to be hanging in the mass in order of 30, 40, 50, 60, and 70, just at the center of gravity. Now, having set up this, the procedure is just on the screen now. You can check out what the procedure is. First of all, we are going to hang this thread at 70 cm from the meter rule. So the length of this thread from here to this point is 70 centimeters. The same with this other arm, also 70 centimeters. And then the thread is to be hung at the 10 cm mark and at the 90 cm mark, as you can see on the meter rule. So that makes the distance between the two threads to be 80 cm. So once this is set up, we can now commence our reading. To take us further, once your setup is complete like this, we are going to make sure that we avoid every form of drought. You take the precaution, ensure that if you need to lock the windows to ensure that there is no wind effect, you take every necessary precaution. Avoid parallax error when you're taking your reading. And then we are going to oscillate this particular meter rule to deduce the time it will take you to make 20 oscillation. So here we are going to make use of our stop clock. In this case, you can see I have my stop clock already at 0 set. So I am going to quickly, just at the center here, give it a small angular displacement and allow it to vibrate in a horizontal position. You can see. So at this point, I am good to go. I can just start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. This is 22.59 seconds. 22.59 seconds. We can still repeat that again because there is a possibility that our answer or our record or our timing may not be exactly so perfect. So you take the time twice. So I'll set it back to 0 and start again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. 22.65. You can see the difference between the first and the second is not actually so much. So with this now, I can increase the mass of this from 30 to 40, and we also take the readings again and see what we are going to get. So having increased the mass now, I can go for another oscillation. So this is the oscillation for 40 grams. So just a small angular oscillation or displacement, and then we are good to go. My stop clock is set at 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. This is 22.25 seconds, 22.25, our first reading. Let's confirm this again. So I start reading again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So this is 22.18. The first one was 22.25, and I have 22.18. So I'll increase the mass from 40 to 50, and we'll find out what we now confirm the trend. You can see that the trend shows that it is coming, the time is reducing as the tension on the spring increases. So I've increased this to 50 grams, and I'm set for oscillation. So I will displace it horizontally, and I'll be good to go. So my time is at 0, and I'm good to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. This is 21.37 seconds. 21.37 seconds, just to be so sure that what I have is correct. I'll repeat this, so I'm good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. This is 21.71, 21.37, 21.71. So let's record this. That's what we got. So it shows that the trend is decreasing. So I've increased the mass from 50 to 60. This is our second to the last reading. So quickly I will displace, and then we go. Ensure that your displacement is not wobbling. Ensure that it is not gyrating. Just simple horizontal displacement. Okay, so I've gotten what I want. So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. This is 21.31. Okay, let me still use this vibration. I think it's still okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. 21.12 seconds. So let me record this for the 60, and then we do our last one. So I have my last mass inserted here to be a total of 70 grams, as you can see here. So let us confirm what our reading is going to be. So I want to be so sure that my oscillation is okay. All right, so I think I have what I want. I have here set at 0 as well. So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This is 20.71. Let me still use it again. Let me use the same oscillation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20.75. So you can see 20.71, 20.75. Now that we have gotten our readings, the next thing that we would have would be to tabulate our readings. I'm going to show you what the table looks like, and from there, from the graph, we can now deduce the mass of this particular meter. Remember, we've already done the measurement using a chemical beam balance. So what we are going to get from the graph is supposed to correspond, although there's a tolerance for our reading. So let's see whether our value is going to correspond with the original reading from the measurement using a chemical beam balance. Okay, so in this experiment also we are expected to deduce the mass of this meter rule. So I have a complete 1 cm meter rule here. So I will be finding the mass, and I'm using this chemical beam balance here. You can see that the initial mass is 0. So all I'm going to do is just to drop this thing on top of it and then take note of the mass. So I have here the mass of the meter rule to be 173.09 grams. So I'm going to record this, and then at the end of the day we'll use it to do some comparisons at the end of the experiment. So here is what our table has looks like. You can see from this table that all the values are being compiled. The mass we used for this experiment, 30, 40, 50, 60, and 70, are all in grams. We had to take the reading of the time twice to ensure accuracy. So we found the mean by adding the both of them, T1 and T2, and dividing by 2. You can see the column, the row for the mean. And then we found the period, which is the mean divided by the number of oscillation, which was 20 during the experiment, and we recorded that also in seconds. We were asked to find t squared, that is the period squared, which we did. We squared and recorded in the correct decimal points and the units. And of course, finally, we were asked to find the inverse of t squared, and we also did that accordingly, and we have it here recorded. So with this, we are asked to plot a graph of t raised to the power of minus 2, that is the inverse of t squared, against m. So if you can see here, you can see that the graph is a straight line graph, and a very neat graph, where we have our values deduced, which we can use to generate our slope. It makes an intercept with the horizontal axis. So from here we got our values for which we calculated our slope. You can check our triangle. So the slope, which is the change in the inverse of t squared to ratio of the change in inverse of t squared to the ratio of the mass, we got our slope to be 0.003824 per second squared per gram. But that is not where the journey ends. We were asked to evaluate Q. Here, Q now represents the mass of the meter rule. So Q, a value was given to us, a deduced value, which is given to us as 0.68 divided by the slope. The essence of this is to help us get the mass of the meter rule. If you're able to punch this accurately and get anything close to the mass of the meter rule, then that means your experiment was actually very perfect. So from what we did here, we found the value after substituting the slope and dividing the slope with using the slope to divide 0.68, we got approximately 177.82. And we know that the value of Q here corresponds with the value of the mass of the meter rule. And initially we showed you that the mass of our meter rule is 173.09 grams. So we have a difference of about 4 grams. And of course, our tolerance is just about plus or minus 10 grams. So it means that our value falls within the tolerance value. So we can assume to be correct. You can try this. Of course, I know you understand the reason why we did not get exactly the mass of the meter rule, which we measured using the chemical beam balance to be 173.09. We are getting 177.82. So the implication of that is that during the experiment, there were some things that we may have not controlled that led to the value being excessive. Some experimental error, maybe during the oscillation, maybe during the recording, maybe during avoidance of precaution during the experiment. So all this can attribute and contribute to your result being a little bit varied. But from what we have, I am not so sure that it is so far from the expected value. Remember that during the course of the experiment, we showed you, we were telling you or reminding you about the precautions to follow. One of them was that we ensured that the threads were firm and tight. Use a split cork to hold it so that it doesn't just slide, and then ensure the support of the pendulum were rigid. Avoid parallax error in reading the meter rule or stop clock, and ensure smooth regular oscillation during the horizontal oscillation, and then avoid drought wind effect. Okay, some other questions we may encounter in this experiment would be to mention some examples of simple harmonic motion other than the motion of a simple pendulum. Of course, you know that simple pendulum is one of the most used examples of simple harmonic motion. But in this case, they don't want simple pendulum motion. They just want the motion other than this simple pendulum. We have motion of a steel ball in a curved dish. We have motion of a seesaw. We have motion of a sounded or vibrating tuning fork. We have a liquid performing oscillation in a U-tube and with a small amplitude. We have a body at the end of a spring performing vertical oscillations with small amplitude. We have a floating loaded test tube suspended in a liquid. We have a vibrating loaded ball clamped to a bench, and so many more examples. You can see we did not mention the motion of a simple pendulum. In this experiment or in this particular question, they don't want you to mention simple pendulum. Also, what is the center of gravity of a body? What is the center of gravity of a body? You see that the center of gravity of a body is that point through which the resultant weight of that particular body acts from, or the point in an object where the distribution of weight is equal in all directions, and it depends on gravitational field. In fact, there are so many questions they can ask, but for sake of time, we may just make do with these two that we have here. So I'd like you to perform this experiment yourself, see whether you can be able to deduce the mass of the meter rule and compare it with the result that we have. I believe that this particular experiment has been of help to you in trying to deduce the mass of an object, which is the meter rule in this case. Until next time, I would like you to subscribe to our channel, like our videos, and share with your friends. God bless you.